Now I would request Mr. Vignesh Ramanan, Honorary Secretary, Chennai Chapter IAF, to introduce the sixth speaker of the day, Mr. R. Veera Vignesh, Manager, Application, SNAM Alloys R&D Center, to our audience.
Good afternoon, gentlemen. Hope you all had a great lunch. So now we need your full attention for the next technical presentation, which is being made by Mr. R. Veera Vignesh. Mr. Veera Vignesh is the Application Manager at SNAM Alloys Pvt Ltd. R&D Center. He is a BE Metallical Engineering graduate from the Government College of Engineering, Salem, 2014 batch. Roles and responsibilities are attending to customer queries on performance and development of products, providing technical support to the marketing team, conducting customer and product trials, coordination with quality and analysis for root cause analysis of defects occurring at customer end, developments of new products to aid foundry process control improvement. He has an overall experience of 8.5 years in experience at SNAM Alloys Pvt Ltd. In product application, mechanical testing of cast iron, mechanical analysis, metallurgical analysis of cast iron, gray and ductile iron microscopy, chemical analysis, defect analysis of cast iron, thermal analysis of cast iron. So it is indeed a pleasure to have Veera with us, and I am sure you will have a great learning experience.
Hope I'm audible. I'm a bit loud, so I just stay away from my mic. Okay. I thank IAF for giving this opportunity to stand in front of the most esteemed Foundrymen of India. And okay, I'm just going to take you through what is inoculation, why inoculation, and where did this evolve from. Okay, I am from SNAM Alloys. We are in partnership with foundry industry for more than 35 years. And I once again thank for the video. Thank you all for giving me this opportunity. I'll continue with my presentation. So can anyone tell me what was the first ever inoculant used? I just want to make it, it's just going to be a history of inoculation. So it's very true, sir. So the first ever inoculant was foundry sweeping. It was by mistake. People have collected the foundry sweeping, and by mistake they have added to the cast iron, and they found that particular heat of castings were giving better results. I was not even born in this time, but I read through articles. So this happened in this foundry called Ross Meehan Foundry in USA, and when they analyzed all these castings, when they came up that the casting results have come up very good, and then they started analyzing what this change could have happened, and they analyzed these results, and they found calcium silicide as a major component of their mix, which the foundry sweepings contained. So they later patented the technology, and they call that as Meehanite iron. That is, iron produced with that particular mixture giving good results is called Meehanite iron. It is patented technology. So this is the basic ingredients of first inoculant ever made: a graphite powder, crystalline graphite powder, calcium silicide, and crushed phyllosilicon. But we don't have any of these three things, or in combination, being used today. I'll just take you through why it is not being used. Graphite used in inoculant mixture should be generally highly crystalline in form to give its best effect, because crystalline graphite tends to give you better nuclei, which is again going to give you graphite nucleation. So, but what we have today, or crystalline graphite availability and expensiveness comes into picture, and the source of crystalline graphite is generally naturally occurring graphite and graphite electrode scrap, which is generally non-uniform or less uniform in its properties. Though graphite by itself is a graphite promoter or a graphitizer, they gave very inconsistent results because of its varying chemical composition and its impurity content. And one more thing, we operate at a temperature of around 1500 degrees Celsius, at which this does not melt or does not dissolve completely. Next is calcium silicide. Calcium silicon both are useful elements to cast iron, but the problem is calcium silicide comes with impurities. There are oxides and some other silicate compounds which covers the calcium silicide generally available raw material or as material available to be used. These impurities create inclusion defects. So this comes with impurities. So as we are working on ppm level defect or rejection levels, this cannot be used. Next is ferrosilicon. Ferrosilicon is a silicon source for cast iron industry. They add ferrosilicon to increase the base silicon content to meet the required desired properties, like it can be a grey cast iron or a ductile iron. But the problem with ferrosilicon is, ferrosilicon gives you silicon, silicon gives you some effect in graphitization, but which is not completely sustainable or not suitable for the variety of castings what we manufacture today. So in that case, why today's inoculants are ferrosilicon based? So we need a carrier inoculant, or we need carrier system which can take away the inoculating elements or special elements we tend to add or we want to add to get the desired properties. So ferrosilicon melts at 1220 degrees Celsius around, and we add all these special elements to this ferrosilicon, and then we use ferrosilicon as a carrier material into the cast iron liquid metal. So there is another compound called silicon carbide, and why that contains silicon and carbon, why cannot not be used for inoculation? Because silicon carbide, again, the melting temperature, the impurities present in it, and there can be a possibility of inconsistent dissolution happening because of the characteristics of the material as well as the process of the foundry by itself. So these are different modern day inoculants available. So these are different elemental combinations, either individually or in combination with other elements, are being used in today's foundry industry to manufacture the thinnest till the thickest castings available today. And all of these are ferrosilicon based. So these are the varieties available, and you may add iron silicon to it. So iron silicon may be contributing to 60 to 70% of the total weight by weight, and the balance will be these elements. So you see in periodic table, the elements present to the leftmost, the most oxidizing elements are the elements which can react very faster, and whatever is closer to oxygen. So these are the elements which are chosen to be used as inoculating elements because they have a very high reactivity and oxidizing and silicate forming tendency. So if these elements have been identified, and if cannot these elements be added in pure form, like can I add pure bismuth, pure silicon, pure aluminum, pure zirconium as inoculants? Pure elements sometimes have higher melting point. The reason why we go for a alloying system is we utilize we maximize the properties which a single element can give or a pure element can give, and we supplement the negative effects with the other elements present in the alloying system. Say for example, iron silicon, when we consider iron carbon or pure iron have got a rusting tendency better. When you add carbon to it, you increase the castability of iron. So when you compare pure iron, cast iron or iron with excess carbon, it increases the castability and it reduces the shrinking tendency, it reduces the corrosion resistance. So these properties are enhanced by the elements we add as alloyings. So in some cases pure elements help, and in some cases pure elements have its own negative impacts, and ferrosilicon is used as a balancing element for all these negative impacts. See for example bismuth, or in ductile iron production there is an element called magnesium, the most important element being used. Magnesium is basically a carbide promoter. So the moment you add magnesium, it kills the metal completely at whatever level be. Say 0.4, 0.2, 0.3, 0.8 or even 0.1, it kills the metal completely. So that is the reason why there is a demand for high inoculation levels with respect to ductile iron foundries when compared to grey cast iron foundries. It is because the element magnesium is added. We cannot run the foundry without element or element magnesium or element closer to magnesium like cerium, lanthanum kind of. So why do we have these many type of inoculants available? So I just want to stop it here. Let us go back to our normal daily life. Initially maybe 1 generation, 2 generations before, there used to be only one doctor in a locality who could treat all the diseases. So one tablet, one solution for all the diseases. So today we have so many number of organs in our body, and there are every specialists available for every different organ. For the eyes, for the nose, for the mouth, for the ear, head, throat, stomach. So that is how, when the casting variety improved, when the castability improved, when more amount of other manufacturing components, other route of manufacturing got converted into castings. So we started looking at complexities in the casting with respect to chemistry, with respect to properties required, with respect to yield, with respect to costing. There was huge amount of requirement of the uniformity in the casting. Say for example, today people are talking of getting the same amount of nodule count in a very thin section casting to the very thick section casting. So I should have one inoculant which can serve shrinkage control in one section, and the same inoculant should serve carbide control in another section. So when these kind of multiple requirements come up, these kind of multiple elements are being required to be added as inoculating elements. So I've just made a simple table, factors that led to evolution of inoculants. One is design factors, variety of castings. So we have started making the largest till the smallest casting ever made, varying casting section thicknesses. So when we work on cost optimization, energy optimization, so we keep reducing the section thicknesses but not compromising on the properties required or the functionality of the component, and increase in complexity. That means thin, thick sections which we thought could not be a possible casting material maybe 5-10 years ago. Today we are able to do it. In the morning presentations we were talking of almost a zero machining allowance. That means you can actually cast the exact component you want to be in service. So with different types of core materials available. So there are such kind of advancements happening. So casting complexity has led to the evolution of inoculants. Metallurgical factors, again, the raw materials. So your final taste of the food depends on the quality of the raw material, or the choice of raw material, or the ratio of the raw material, or the sequence, or the way these ingredients or raw materials are being used and utilized. So when the quality of raw material changes, say for example, when steel scrap prices shoot up, we tend to use our returns more, and when we get exhausted with returns, and when steel scrap comes down, we start using steel scrap more. Or when you have a machine shop attached to our own foundry, we start using borings, telling that we get alloying elements back into our metal. So requirement of ferroalloy addition comes down. So there are a lot of factors involved in varying or altering the charge mix to get the same quality. But the actual problem is, though you may be able to get the same chemical composition as we have been getting with a different charge mix, but when you try to add when you try to add different ingredients and make a casting, the property of the casting or the functionality of the casting can have a small variation between the one made with a different charge mix and the other one with a different charge mix. Tramp elements level. So today you would have seen maybe 10-15 years ago there was no niobium in steel. Today Tata, Jindal, they are talking of niobium in steel because they want to do something innovative. They have added element niobium. So today if we are purchasing some scrap which would have been from Jindal or Tata, will definitely have some niobium. Or mild steel, what we talk of today, and mild steel what would have been 10 years back or 15 years back is completely different, because every industry is evolving by itself. So the tramp elements level in the liquid metal which is introduced through the process, through the raw material, keeps varying continuously. And but our customer's target is zero defect. That means all the castings you produce should be 100% defect free, but whatever be the cost. Stringent requirements from customers over time. Actually this line means everything else. So the customers have, I've heard from my foundry friends that customers have been squeezing to get the maximum benefit out of the casting. So that's one way. As a person, when I drive in a car or when I go in a bus, I see there is an engine block placed inside it. So somebody in OEM would have thought that this engine block should not fail and the life of the passengers to be taken care of. So that is the ultimate meaning of when customer asks for zero defect. Say for example, if there is a defective casting, by chance, by mistake, with it's carried over to a tractor or a bus, or any of our family members travel in it. So let us, hopefully, God's grace, nothing like that happens, but stringent customer requirements may be because of cost or maybe because of the functionality requirement also. And advancements in engineering is making all the tolerances tightened. Just made a synopsis. So initially the castings got converted from forgings, whatever components which were forged. So when we tried to match the same elongation, same yield strength, but compromising something on the strength, people started converting forgings into castings. So that is how some of the steel grades can be directly replaced by a cast ductile iron material. So when initial castings got changed into forgings, the initial set of inoculant would have been sufficient. When different grades of castings were required, a single alloy, maybe a composite of everything would have been sufficient. And a single alloy made with different element form of mixture, say for example manganese, copper, and varying section thickness come up, a new inoculating type would have come. And when the productivity increases, when this, in this scenario, if the castings were performing well and they wanted more castings, and productivity requirement came up, say, then you wanted to pour more boxes, more casting, so long pouring time, sustainability of the property of the liquid metal and casting throughout the time, barium or calcium inoculant would have come up. And when varying section thickness come up in heavy sections or thin section castings, zirconium inoculant. So these are some of the requirements and evolutions of casting industries and how these inoculating elements would have appeared or is in relationship with the evolution of casting industry. So method of inoculation, it is number one is the selection of inoculant and number two is the way you handle the inoculant. So I call handling of inoculant as buying the inoculant, taking the inoculant, weighing the inoculant, adding the inoculant. So everything put together is called as handling the inoculant. So initially it would have been a single stage, and when the importance of inoculation effectiveness came into picture, the fading phenomena was understood when you started to pour greater than 4 minutes, greater than 6 minutes, greater than 8 minutes, then the fading tendency or variation in the properties with respect to time of filling or pouring came up. So then the fading phenomena was understood. Once you understand the fading phenomena, then you wanted to get the same properties at the last box pouring also. So we tried to either split the inoculant or do a separate inoculation at the end. So late inoculation, and when late inoculation comes into picture, how do you add late inoculant? Either you add it manually, or you have a automatic weighing system and dispensing system, or you have an inoculation done inside the mold, which we call as in-mold inoculation technology. Okay, we have been talking of inoculation in liquid metal after furnace. Can we do inoculation at the furnace itself? Yes, it is possible. You can call it as conditioning of the liquid metal. So this, whatever changes or whatever demand of inoculation or improved or varying levels of elements in the inoculation materials have come up due to the varying potency of the raw material or potency of the liquid metal by itself. So if we can control the furnace metal directly, then you can actually control or work on the optimization of inoculation levels and the elements you want in your inoculant. So there are materials called as preconditioners, that means it will condition your liquid metal. So it is like, say for example, Monday, Tuesday, Wednesday, Thursday, Friday, on all 6 days, the first heat will always be different. So the first heat, the second heat, the third heat, though the chemical composition is same, with respect to time, temperature, holding time in the furnace, melting rate, the potency of material can vary slightly. And people who have got this holding furnace kind of, there is a tendency that metal from different furnaces can get mixed up and metal with different potencies get mixed up. So in that cases, to balance the variations, we can do inoculation at the furnace itself. It is called as conditioning your material. It is generally termed as preconditioners. So can I produce castine without inoculation? Yes, possible. But the problem is you will be lacking the uniformity. It does not mean that you don't add inoculant, you end up with 100% carbides. No. Your liquid metal by itself will be having around 50 to 60% of the potency to produce enough graphitization. The problem is because of varying section thickness, because of the cooling rate, and because of the profile of the casting, the same carbon equivalent works different way at different locations. So inoculation is added to ensure that you get uniformity, that means non-defect structures throughout the castings, at least bare minimum. So if you don't inoculate, you will be getting uninoculated, that means undercooled graphite, not 100%, but maybe at all the hotspot locations or fast cooling locations, which might be a working location of the final functionality. And uneven graphite precipitation. So that means you might be having the same amount of carbon here and here, but the amount of nodules formed in case of ductile end may vary. And shrinkage tendency is not controlled. Sometimes this variation can come up if you do not inoculate. And undercooling. So all these parameters are related to one another. Again, can inoculation alone guarantee a shrinkage-free casting? No. Actually, inoculation is just a complement, or it is just an add-on we do. So the basic characteristics or shrinkage is a solidification phenomena. That means a void created where your liquid metal is not potent enough to fill the entire liquid, entire cavity or entire shape of the component within the stipulated time at the given temperature also. So when the rate of solidification is determined by your methoding and chemistry, inoculation supports it. Say for example, any variation coming up in the pouring temperature, or any variation coming in the carbon equivalent, or any variation coming in the filling time, or heat extraction capability of the mold or the cores or the coating, inoculation supports. What inoculation does is, say for example, a carbon with a ductylene with a 3.5 carbon, 2.4 silicon will be giving you, say for example, X amount of nuclei. Sometimes this X can become X minus X minus delta X or X minus delta X1. This delta X1 is given by the inoculant. Even you do not add the inoculation, you will still be getting with that X minus delta X. But this delta X keeps varying heat to heat, and you might not be able to attribute to any of your foundry parameters directly. So to avoid this variation, inoculation helps. But the major shrinkage-free casting or a void-free or defect-free casting should start with the characteristics of the metal or the foundry itself. That is the methoding, the design, the environment of the foundry or the casting, and liquid metal. So these are different list of elements, like different inoculating materials available with varying elements, and I've made a broad classification with our experience, like how do we select inoculation with respect to what is the property you expect, or what is the property you want, or what is the variation you are facing today. Say for example, if you have a very thin, thick, and both combination casting section thickness, you can opt for these inoculations, and all inoculations suit to that particular foundry, that particular metal only. Say for example, a foundry A producing the same component, foundry B producing the same component might not be able to produce with the same inoculant or the same addition rate of the inoculant. So it is like the medicine what you take, it should suit your body conditions rather than a common medicine which is going to cure or is going to be a cure for everybody. So all these are arrived out of trial and error and establishment basis only. I'm putting a clause beneath. This is again a ductile inoculation selection. So with respect to varying levels, your pouring time, tapping temperature, and the method of inoculation, you can select different inoculating elements and inoculant types. And you can always contact SNAM. We are always there for support in establishing the right inoculation practice required for your castings. So we come with experiences gathered from good foundries, good practices, but we ensure that only the science gets transferred. So it is just the casting science. So how do people evaluate inoculants, or how are inoculants efficiency being evaluated? There is chill test. It's a very old known test, and I've heard people telling that, but just by looking at the width of the chill, they will be able to predict and exactly adjust the carbon level, carbon equivalent level, and they can even predict the carbide forming tendency in the casting. And eutectic cell count. So this is directly measure of the number of nuclei available. So it is expected, or it is bound to increase after inoculation, and any changes with respect to the melting practice or temperature gradient, eutectic cell count alters. Though you get the same chemical composition in a spectrometer or CE meter, still eutectic cell count can vary between heat to heat, tapping to tapping from the same furnace. And undercooling measured using thermal analysis. This is that I should not call this as an emerging term. We have been using this for years together, and it is like your ECG. So what your conventional testing cannot tell, thermal analysis will be able to tell you. Microstructural properties, these are the final responses what a customer relates it with his end properties. Say for example, strength, yield strength, low temperature impact resistance. So all are related to the microstructural entities. Nodule count, everybody expects 0 carbides, or if allowed in the workable range, nodule count or type of graphite flakes and amount of graphite flakes. Distribution of nodules, the size of nodules, in the same way in grey casting as distribution of graphite flakes and type of graphite flakes and the amount of graphite flakes. Mechanical properties, uniformity throughout the casting. It is the catch is uniformity, and what inoculation can give you is uniformity only. Machinability, tool life, and if this is the output of all these previous parameters. So what happens when excess inoculant is added? So the list of elements what I had proposed previously, what I have shown previously, are strong oxidizing elements. So by default, when you take liquid metal to a temperature close to 1600, oxygen influx happens and you start getting oxides in your liquid metal, nascent oxygen. The time when the temperature comes down, oxygen cannot stay, it starts reacting with elements present in the liquid metal and form compounds. So we can call it as oxides, you can call it as slag, or slag is made of silicates. Silicate is again an oxidized form of silicon. So ultimately it revolves around oxygen. So we form compounds. So we can call it as oxides, you can call it as slag, or slag is made of silicates. Silicate is again an oxidized form of silicon. So ultimately it revolves around oxygen. So these are the ill effects of, I've come to the last slide. These are the ill effects of inoculating elements. What happens when you overdo your inoculation? So it's overdosing. Too many sleeping pills will take you to the forever sleep stage. So excess of cerium and lanthanum, excess of bismuth, excess of titanium has got, these are the ill effects of its own, the individual elements characteristics. So hydrogen pinhole tendency, aluminium. Actually aluminium is, you can call it as a catalyst. So that does not mean increasing aluminium will give you pinhole. When you have surroundings where you have got a high moisture and a lot of gases coming from the mold and the liquid metal and less permeability, in that case when high aluminium is present, then it can lead to a pinhole. So we even have a variety of inoculant which contains 4%, 5% aluminium, which is successfully being used in manufacture of gray and ductile and casting. So it is not that high aluminium, it is the environment around present, and with this presence of high aluminium can create pinholes, or it can, I should call it as, aggravate the severity of pinhole. So I have introduced you to the past and present inoculation types. So tomorrow we might not be knowing, so we are talking of EVs today. Can be a new process, can be new inoculating elements, can be non-availability of inoculating elements come up, but do not worry, we are always there. Thank you.
It is open for questions. Any questions, please raise your hand.
0.8 to 1.2 aluminum is a correct number, because beyond 0.1 to 1.2 we had some increase of linkage and below chillness effect.
Yes, sir.
So what is optimum, how aluminum content, how does it play?
Sir, sir, I have any inoculant, say for example the aluminum inoculant will have iron, silicon, calcium, aluminum. It can be other elements, or we need not have the other elements. So if we have this 4 component system, the reactivity of your liquid metal and the oxidizing potential of these elements are to be looked into when I choose an inoculant, say for example. Say if I give you a barium inoculant, might be your amount of oxygen available in your metal or your characteristics of liquid metal might not be as compatible with barium's reactivity. So when you say, there are some people who require aluminum, because aluminum has got a equal or stable oxidizing potential as that of calcium and barium. So barium is a bigger atom, aluminum is not a bigger atom, but aluminum's reactive tendency for a given temperature is more. So for example, some foundry conditions with respect to liquid metal, I am not talking of the casting or the severity of the casting or the size and section thickness of the casting. So the health of liquid metal determines what inoculating element can be selected and to what level it can be added. So it is basically your potency of liquid metal. Amount of dissolved oxygen I can tell directly, but there is no measure right now available, sir. So it has been arrived at different trial and errors, and inoculant with less than 0.5 aluminum, there is no existing inoculant like that. So it is like silicon is balanced by calcium, silicon calcium is balanced by aluminum, and this combination gives you some effect. So it is arrived at that level, sir.
Okay, the second question I know it answered by, as you told earlier, that the current mess scrap we are getting, we are also facing that of late. What does that mean? That because the OEMs are trying for a higher strength or higher performance base, we are getting the scrap with higher moly, chromium and vanadium also.
Yes.
So in this case, any solution there through inoculation?
Sir, sir, these are elements similar to iron which cannot be done anything with respect to inoculating elements. What inoculating elements can do is, it can react with whatever is not required for your casting. Say for example, oxygen, sulfur, phosphorus, nitrogen. These elements have got affinity towards these reactive, like electronegative elements, like the elements which come to the right side of the periodic table. So moly, vanadium, chromium are equivalent to iron. So as dense or even denser than iron. So what we can ensure in our liquid metal or even our solidification is, we can avoid forming network of carbates of all these elements. So what happens is, it is not just molybdenum carbate gives you failure. It is network of molybdenum carbates which is giving you failure. So if we understand why networking of molybdenum carbates happen, so it is the cooling rate of casting decides how the molybdenum carbate forms and gets liquid. Generally, all these carbate forming elements will be located around the grain boundaries. So if we can ensure that our cooling rate of the casting is maintained such that the molybdenum carbates are not pushed towards the grain boundaries or sudden chilling does not happen, we can avoid the severity of molybdenum, chromium, vanadium, these carbate forming elements. There are usefulness of all these elements. These increases your high temperature creep resistance, what we call in engine blocks and CMO castings. But the network of all these elements or all these compounds are dangerous. So inoculant does not have any part to do with that, sir. It has to do with the solidification pattern of the liquid metal in the casting, sir.
Thank you.
Thank you, sir. Thanks for the lovely answers.
What is the qualification method for the inoculant or the measurement of the nucleation potential? Say, does the charge variation will be there?
Sir, no change in your defect or rejection percentage, sir. With respect to the same property which you are measuring, no change in or reduction in your rejection percentage related to metallurgical factors, not pouring defects, sir. Say if your carbide percentage come down, your steadite percentage comes down, or your type D percentage comes down, or your uniformity nodule count increases, then those are the measures of inoculations.
After the production.
Yes, sir.
You told about Tata adding inoculation.
And niobium, yes.
What is the contribution of that?
Sir, sir, we do not know what niobium does to cast iron. So that's a threat. I just want to stop it there because I do not have any information on that. We do not know what niobium does to cast iron. That much, sir. If I get anything, I'll definitely share in the forum. Thank you, sir.
Thank you everyone for the lovely questions. Thank you for the lovely speech, sir. As mentioned, you were not born when inoculants were found, but you have brought the subject alive. So thank you a lot. Now I would wish to have Mr. Dayalan on stage to felicitate Mr. Veera Vignesh with an Angavastram. Now I request Mr. S. Sundaresan, Senior Vice President, Brakes India Foundry Division, to please provide the speaker with the memento.